Good chocolate right out of the wrapper has an attractive sheen and a satisfying snap when you bite into it. But when you melt that chocolate, it sets up into a soft, blotchy, dull-looking mess that melts really easily on your fingers. Why the big difference? The short answer is that the crystal structure of the cocoa butter in the chocolate has changed. The differences are pretty easy to spot, but the science at work is actually quite complex. When cocoa butter solidifies, it can form any of 6 different types of crystals. Each of these has a different melting point, density, and level of stability. To prevent the kind of problems we just talked about, you want as much of the cocoa butter as possible to form one particular type of crystal, called beta crystals. And we want them to be as small as possible, because that way they'll produce chocolate that sets up dense, shiny, and snaps cleanly, like this bar here. Beta crystals are also highly stable, so the chocolate composed primarily of them will change very little over a long period of time, even months. Finally, beta crystals have a higher melting point than less stable crystals, which means the chocolate won't melt on your fingers. So, we know that we want beta crystals, but that leaves us with the question of how do we get them? The traditional way to ensure very small beta crystal formation is known as tempering. First, the chocolate is melted so that all of its fat crystals dissolve. It's then cooled relatively quickly and with a fair amount of agitation to encourage small crystals to form. At this point, the chocolate contains a mixture of several different types of cocoa butter crystals. Some desirable beta crystals, but also a lot of unstable ones. Here I have a model of this form of chocolate. The Legos represent stable beta crystals, while the ice cubes represent a range of unstable crystals. Next, the chocolate is heated to just under the melting point of the beta crystals, right around 88 degrees. Now what this does is melt these unstable crystals while preserving the beta crystals. Finally, upon cooling, these seed crystals trigger the formation of more beta crystals that eventually form a dense, hard, glossy network. Here's a piece of chocolate that I tempered this way here in the test kitchen. Now as you can see, it displays all of the desirable characteristics. It's shiny, it snaps cleanly, and it doesn't melt on my fingers. This is the science of good cooking.